Okay, well, the way we're going to do that is by using the density properties of rock and the properties of sound waves. So if we take an analogy and we look at how light passes through a prism, up in the top right-hand corner, we see that white light goes into a prism. It is refracted to a lesser angle as it passes through the first wall, and then as it passes through the second wall, it's actually split into the colors of the visible light spectrum, Roy G. Biv. Same principle of why we see those colors in a rainbow. Because we know what the characteristics of light are, we can back measure what the angle of the wall of the prism is at. So by observing the light coming into one side and observing the light coming out of the other side, we can take those characteristics to determine what the characteristics of the medium the light passed through was. The same is true of earth materials. Instead of using light, we are using seismic waves or shock waves. As a seismic wave leaves a source, in this case where we've got this image, the source is an air gun that's in the water. As it creates a very large boom, those vibrations travel down through the water into the bedrock of the ocean floor and then bounce off of various layers and return to be heard by these hydrophones that are dragged behind the boat. Since we know when the shock wave fired, we know when the air gun went off, and we know when the hydrophones received the following reflected shock wave, we can then deduce how far down whatever the shock wave bounced off of is. So what we've done is look at when the shock wave leaves the source and when and where the shock wave is recorded to deduce what the subsurface of the ocean floor looks like. It's a fairly simple idea, but in practice can get very, very complicated. But it is very, very widely used, especially in the search for oil, and is used to determine the physical properties of the Earth's internal layers.